Our oceans are in crisis. Pollution, climate change, and environmental neglect are degrading marine ecosystems at an alarming rate. But to fight this decline, we need data, real-time, accurate, and widespread. Current monitoring methods are expensive, limited, or require heavy human intervention. That's where we come in.
I'm Quinlan Reed. I'm the team lead for the project, and I'm also the software engineer.
My name is Jennifer Hall. I'm one of the mechanical engineers and the procurement lead.
Hello, I'm Jason Mayhall. I'm the mechanical lead and also the aerospace engineer.
My name is John Goodale. I'm the team integration lead and the team's systems engineer.
I'm Zach Borman, and I'm the electrical and computer engineer on the team.
I'm Cooper Malden, and I'm one of the mechanical engineers.
Hello, my name is Yadi Jimenez, and I'm the biomedical engineer on the team.
Our mission, to develop a cost-effective, self-riding aquatic drone that autonomously collects critical ocean data, starting with temperature, a key indicator of ocean health. The AQUABOT Fluence is designed to be hydrodynamic for minimal drag, self-riding to survive rough seas, and equipped with real-time satellite communication, all while being affordable for widespread use.
The actual design of our hull is inspired by the US Coast Guard patrol boats and self-riding lifeboats used all around the world. We used SolidWorks to model the hull and decided to pursue a two-piece design so that we can easily access the electrical and propulsion components of the AQUABOT. We created a scaled proof of concept via 3D printing to test the self-riding and buoyancy properties of the design. But for our full-scale product, we decided to use fiberglass casting, as this is the industry standard for small-scale boat manufacturing. The brain of the system sits on two acrylic shelves mounted to runners casted into the bottom of the boat. Each electrical component sits on 3D printed TPU bushings to mitigate shock associated with impact.
Huzzah! Yes.
After cold calling several boat shops over winter break, Eddie's inboard marine equipment was the first to call back, and a subsequent meeting with Eddie proved pivotal. Eddie's enthusiasm and practical insights significantly shaped our design, leading to crucial changes like optimizing the sensor housing and adopting a two-piece hull construction. He also directed us to help find a self-sealing rudder stuffing box and propeller shaft. To stay within budget and save time, Eddie suggested 3D printing the plug. However, initial attempts to print the plug at the EDC were unsuccessful due to size limitations. I was able to coordinate with Orion Labs, LLC, to successfully print the plug and also help make the brass tube sensor assembly. This plug was then given to Eddie's Inboard Marine, where they added the finishing touches. As of filming, we are awaiting the completion of the final fiberglass boat, and the process will leave us with both a boat and a reusable plug for future production.
So for our electrical system, it is going to be divided into two main subsystems, which are the propulsion subsystem and the sensor subsystem. The propulsion system includes a brushless motor, a servo motor, which control the propeller and rudder respectively. The sensor subsystem consists of the GPS, IMU, and temperature sensor. The entire electrical system is powered by 3 LiPo batteries. One battery is dedicated to the brushless motor, since it requires significantly more current than the other components. Another battery powers the Starlink unit, which provides Wi-Fi connectivity for our processor. The third battery supplies power to all the remaining smaller electrical components. It does this through step-down DC-DC converters, which ensure each component receives its proper voltage. And lastly, we're using a Raspberry Pi 4 as the main processor for our entire system, which compiles all of our code.
Our temperature sensor is assembled onto a Raspberry Pi and fully coded for deployment. It sends real-time data to our user interface and data storage system, using a custom waterproof brass fitting design to install during fiberglass boat fabrication. We're getting 24 points.
The GNC code for our project is composed of 3 modular components: navigation strap-down, pure pursuit guidance, and a PI controller. The navigation strap-down module processes data from the IMU by integrating accelerations and angular rates, while accounting for the Earth's rotation, Coriolis effect, and sensor bias is estimated by a Kalman filter. Additionally, it incorporates bias corrections from GPS data to refine the integrated estimates. The output of this module includes the vehicle's attitude, velocity, and position vectors in the navigation frame. The pure pursuit guidance module computes the angle between the vehicle's heading vector and the vector pointing from the vehicle to a designated target location as defined by the user. This angle represents the heading error, which serves as the error signal for the controller. PI controller takes this heading error as input and adjusts the rudder angle accordingly. It continues to actuate the rudder until the error is driven to zero, resulting in the vehicle aligning its heading with the direction of the target location.
The graphical user interface subsystem for our project is run locally using Python. When the user runs the groundstation.py file, a pop-up window appears that displays the location of the connected drone on a map interface. The user can then select Start to make the drone begin collecting data, Save to make the drone send its current data to a CSV file the user has access to, and Stop to turn off the drone once it is returned. They can also select points on the map interface to tell the drone where to move to next. The drone and the user interface are both clients connected via a broker on the MQTT system. This makes data transfer easy and scalable, as additional drones can be registered as clients and connected to the ground station with great ease.
Our deliverables for hardware include our MVP1 hull, a reusable fiberglass mold, and our final boat assembly. For software, all in our GitHub repository, we have our SOLIDWORKS CAD files, our GNC code, our GUI files, and our sensor codes. That includes temperature, IMU, and GPS codes. For documentation, we have our user guided manual, our software design document, and our final report.
At this stage in our project, most of our requirements have either been fully met or partially met. We anticipate that within the next few weeks leading up to our final design day, we will have most, if not all, of our requirements fully met. At this stage, the primary lessons we have learned from this project are the importance of communication quickly, early, and often with any outside parties that we may be working with, the importance of flexibility in design, and the importance of starting early on any design prototypes. The AQUABOT Fluence project is a step forward in the maintenance of ocean health. Together, we can turn the tide.